Recursive algorithms. An algorithm is called recursive if it solves a problem by reducing it to an instance of the same problem with a smaller input. As an example one, we'll consider recursive Euclidean algorithm. Procedure GCD, A and B are non-negative integers with A less than B. First row, if A is 0, then GCD of AB is B. Else, GCD of AB is GCD of B mod A, comma A. That is, the first number is the remainder when you divide B by A, so the remainder is strictly less than A. So this requirement is met. Example 2, recursive Fibonacci algorithm. The procedure is called Fibo, and the input is just n, which is a non-negative integer. If n is 0, then return 0. If n is 1, return 1. Else, return Fibo of n minus 1 plus Fibo of n minus 2. So here we have this if condition, then action, else if condition, then another action, else another action. This is more complicated if statement. So if the first condition is true, then return 0. If the first condition is not true, it checks the second condition. If it is true, then returns 1. If neither of this is true, then it comes this action after else. The output is the nth Fibonacci number. How this algorithm works? Say we want to compute f of 4, we call Fibo 4. It calls Fibo 3 and Fibo 2. Fibo 3 calls Fibo 2 and Fibo 2 calls Fibo 1 and Fibo 0. And then Fibo 3 is computed, Fibo 2 calls Fibo 1 and Fibo 0, and we end up with computing the fourth Fibonacci number. How many additions are needed here to compute the fourth Fibonacci number? 1, 2, 3, 4 additions. And here in this table, we have the number of additions needed to compute the first 3. F0 and F1 don't require any addition. F2 requires one addition, we add these two. And F3 requires 2 additions, and we saw that F4 requires 4 additions. But 4 is just F5 minus 1. F5 is 5. Minus 1 is 4. So we can make this conjecture that computing the nth Fibonacci number Fn requires Fn plus 1 minus 1 additions. We can prove this by induction, mathematical induction on n. Assume that Fk requires Fk plus 1 minus 1 additions, and Fk minus 1 requires Fk minus 1 additions. Then Fk is Fk plus Fk minus 1, so it will require Fk plus 1 minus 1 plus Fk minus 1. These are the additions for computing Fk minus 1 and Fk. Plus 1, because we have to add those two numbers. And the result is this sum, which is Fk plus 1 minus 1. And this is exactly what we need to prove. The number of addition required for computing Fk plus 1 with the recursive Fibonacci algorithm is Fk plus 1, the next Fk plus 2, the next Fibonacci number, minus 1. An iterative algorithm for computing Fn. If n is 0, then return 0, else x equals 0, y equals 1, or I from 1 to n minus 1. Z is x plus y. X is equal to y, and y is equal to z. This is the action of the for loop. Return y. This algorithm computes Fn step by step. So the algorithm first has this initialization. X is 0, y is 1. These are F0 and F1. After the first execution of the action of the for loop, X is F1, y is F2. After the second execution of the action of the for loop, X is F2, y is F3. So it takes n minus 1 additions to compute Fn. For every recursive algorithm, there is an equivalent iterative algorithm. Recursive algorithms are often shorter and more elegant and easy to understand than their iterative counterparts. However, iterative algorithms are usually more efficient than in their use in space and time. We know that computing FM with recursive algorithm requires FM plus 1 minus 1 additions, while computing the n Fibonacci number using iterative algorithm requires n minus 1 additions, and if n plus 1 grows faster than n.